In MATLAB, there are many functions that can be used for these sets of equations as matrices and for these linear algebraic equations. And let's define them here quickly. For the matrix analysis, especially the condition number, if you remember, this is important to decide if the matrix is ill-conditioned or not. It can be calculated by cond function. The vector or matrix norm can be calculated by norm. Also, there is rcond. There is another condition estimator. Rank gives us the rank of the matrix and number of linearly independent rows or columns. Determinant can be calculated by det. A trace will give us the sum of diagonal elements. You know, the trace term is defined as the sum of diagonal elements. Null gives us the null space. Orthogonalization is defined by this function, and rref, reduced row echelon form. So for the linear equations, so slash actually is used to solve the equation, this reverse one actually. For Cholesky factorization that we mentioned for symmetric matrices, this is used. For LU actually decomposition, this is used for the factors of Gauss elimination. For inverse, we use this function. QR is the orthogonal triangular decomposition. QR delete is deleting a column from the QR factorization. This is another method that we didn't learn yet, but in the following chapters we will learn about QR factorization as well. QR insert a column in the QR factorization, and then L as non-negative least squares. So this is again for the following chapters we will be learning about least squares. Pseudo inverse is with P, I, and V, and LS co least squares in the presence of non-covariance. So these are basically not related to this chapter, but for the following chapters. But these are necessary for the linear algebraic equations in this chapter that we learned in this and previous chapter as well. In this slide, we have an example 11.5, and we will be using MATLAB for solving linear equations, and this 3x3 linear equation you can see here. And the solution to this system is known as 1, 1, 1. So for this, first we start with separating A and B here. These are, and in MATLAB you can simply write like this and get the A matrix. So the columns, actually the rows are separated from each other, each row by this sign, and B's are these. You can see the same sign, the semicolon, to get this in a one column with rows actually. So after writing these, now we can solve it, but before solving we can check the condition. By condition A, you can see the condition is 366. This is very large. The large value means between 2 and 3 digits of precision could be lost. So this is actually can be a problem actually, a large condition number, but still we will check if it is solved or not. And this result is based on the spectral A2 norm. We mentioned this already before. You can check the relevant topics for this. So let's continue on this solution after getting this condition. So this means we have to be careful, and we will see what it means. But of course, this will still give us a result because these MATLAB functions have good internal numerical approaches that can overcome any issues. So it uses different approaches to be able to overcome issues. Even if this is very large, it's okay to use, but we can only know that 2 or 3 digits of precision can be lost based on this information. So let's move on to the next slide to see the results. We already learned before that we have 2 options in MATLAB to solve the systems of equations. The first one is the backslash. When you divide A by B by the backslash, it actually does the Gauss elimination to solve system. You can see x's are 1, 1, 1. So we calculate it as the true values. Also inverse solution, simply we will get inverse A times B, and it will give us the same solution as well. In this approach, it first determines the matrix inverse, this one, then performs the matrix multiplication here. That's why this is more time consuming than using the backslash approach. We have completed chapter 11, which was about the iterative methods to be able to solve the systems of linear equations. Here you can read chapter 11 in your book for this Gauss-Seidel-Jacobi iteration approaches. Also in chapter 12 there are case studies about linear algebraic equations, solving these. You can study this chapter as well. I will not go to this chapter 12 in the book, but there are examples, further examples here relevant to engineering area as well. You can check them. Also there is the epilogue part, which is a summary of the linear algebraic equation solving approaches. Just summarize formulations and explanations. You can check that too in your book. And thank you very much for listening. See you in another class.